Welcome to the last part of the problem-solving session for part 2 of chapter 11. And we begin where we left off, question 6, which states the following. An ice skater starts to spin with her arms stretched out to her sides. She balances on the tip of one skate and turns without friction. Here, friction would be an external force that might produce a torque to interact with the skater. She then pulls her arms in so that she rotates 2 times as fast. The question is, does her moment of inertia change? If so, by how much? Does her angular momentum change? If so, by how much? And does her rotational kinetic energy change? And if so, by how much? Well, the first thing that we note is that they're telling us that if omega is her initial rotational speed, omega final, after she draws her arms in, will be equal to 2 times her initial value. Now, we use conservation of angular momentum, which tells us that the angular momentum after she brings her arms in should equal the angular momentum before she brought her arms in. So in other words, her moment of inertia finally, after she brings her arms in, times her angular speed of rotation after she brings her arms in, which I'm just going to write as 2 omega, equals her initial moment of inertia, let's just call that I, or I initial, whichever we want, times her initial angular speed, omega. And so what you can see here then is that I final is equal to, these omegas are going to cancel, her initial inertia divided by 2. So the question, does her moment of inertia change? The answer is yes. By how much? It is half as much as her initial moment of inertia. The next question asks, does her angular momentum change? Well, the very concept that allows us to determine her moment of inertia says it all. Angular momentum should not change and therefore be constant. So the answer is a big no. Angular momentum does not change. The last part asks us about her rotational kinetic energy. So let's see. Initially, her rotational kinetic energy would be 1/2 her initial inertia, I, times her initial angular speed, omega squared. The final rotational kinetic energy is 1/2. I final is I over 2. Omega final is 2 times omega squared. And so let's see, what have we got here? We've got 1/2 times, this 2 gets canceled by one of these 2 because this would end up being 4 omega squared, so that becomes a 2. So I have I times omega squared times 2. And so effectively, if this is her initial rotational kinetic energy, 1/2 I omega squared, you can see that the final is twice as large as the initial rotational kinetic energy. So her moment of inertia was half, but her rotational kinetic energy was doubled. Next question. A student sits on a freely rotating stool holding 2 weights, each of mass 3 kilograms. So we have M 3 kilograms here, M 3 kilograms here. When his arms are extended, the weights are 1 meter from his axis of rotation. 1 meter, 1 meter. And he rotates at an initial omega equal to 0.75 radian per second. Now, the moment of inertia of the stool and his torso, I, okay, which would be very difficult for us to calculate, is given to us as 3 kilogram meter squared, okay? And so this is just his torso from, say, shoulders to center and legs to leg, assuming there's no change in the position of his torso after he brings his arms in. Because look, the student pulls the weights to a position of 0.3 meters from the axis of rotation. So now, although it appears it's right at the axis of rotation, in fact, the moment of inertia of the stool and the torso is still 3 kilograms meters per square. The masses of the weights are still 3 kilograms each, so that has not changed. So that's true for both masses. What has changed is that R sub I, which is very difficult, R sub F, we're going to call this the initial location of the masses relative to the axis of rotation. R final is 0.3 meters, and that would be true for both masses as well. So we are asked to determine what is going to be the change in the angular speed of the student and the stool because of this change in the position of the masses. Well, conservation of momentum, angular momentum, will help us work it out. Well, let's see. When he brings his arms in, we have each mass now at 0.3 meters to the axis of rotation. So 2m times r final squared, so m times r final squared plus m gives us 2, plus the moment of inertia of the stool and the torso times omega final equals 2 times mr initial squared, the 1 meter distance, plus I, that I has not changed, times omega initial. So we're solving for omega final. And you can see, okay, let's work with the numerator first. 2 times m is equal to 3 kilograms. So we have 6 kilograms times 1 meter squared plus 3 kilogram meter squared, and this whole thing is multiplied by the initial speed, angular speed, 0.75 radians per second. Denominator, 2 times m, which again gives us 6 kilograms, times, this time 0.3 meters squared, plus 3 kilograms meter squared. And when we put this in our calculator, we should get an omega final, which is equal to 1.91 radians per second. So effectively what has happened is that by bringing his arms in, he has significantly increased his speed of rotation. Why? Because when you see that the angular momentum must remain constant, if this is large, if this becomes smaller than it was initially, then this becomes smaller, that has to become larger, so that the product is still equal to the larger moment of inertia times the smaller initial angular rate of rotation. So this is part A of our problem. In the next part, we're asked to determine, let's see, is there a next part? There is no next part. Okay, so we're good. We've effectively finished this problem. All right, let's go to the next problem. Here, question 8 says, a disk of moment of inertia 0.25 kilogram meters squared is rotating with an initial angular speed of 3 radian per second. There is another disk which is stationary, not rotating, sitting at some distance above the disk number 1. But very shortly after the disk will drop down onto disk 1, and both now, I1 plus I2, will be rotating with a common omega final. So in other words, this is like a collision where you had an M1 which was moving and M2 was initially at rest. They collide with each other, they stay locked like the two cars whose bumpers got locked, and they move with a common final velocity. This is no different than that, and we're asked to determine the final common velocity and the initial and final rotational energies, and this is why I was thinking the previous problem had a part B. All right, so let's get part A first. Well, let's see, we have I1 times omega 1 initial plus I2 omega 2 initial, which is 0, and we didn't have to write it, but why not? I1 plus I2 times omega final. All right, that means now we're going to plug in some numbers. Omega final is equal to I1 0.25 kilogram meter squared times omega 1 initial, which was 3 radians per second, divided by I1 plus I2, which is 0.35, 0.1 plus 0.25 kilogram meter squared. That gives us an omega final, which is equal to, let's see, 2.14 radian per second. And that makes sense. Initially, when it was just one disk rotating, it was able to rotate at 3 radians per second. Now both disks have to rotate, and so because the inertia has gone up, the speed of rotation has to go down. Okay, initial rotational kinetic energy is simply just due to disk number 1, I1, omega 1 initial squared. Plug in some numbers, we get a half 0.25 kilogram meters squared times 3 radian per second squared, and that gives us a value of 1.125 joules. All right, K rotational final, 1/2 I1 plus I2 times omega final squared, 1/2 times 0.35 kilogram meter squared times 2.14 radians per second, the whole thing squared, gives us a final rotational kinetic energy of 0.804 joules. So some kinetic energy has been lost in the process of that collision. Okay, last problem is a Kepler's second law problem. If you recall, Kepler's second law told us that the radius vector that connects a planet with the sun sweeps out equal areas in equal intervals of time. Now that statement right there was translated to mean that when a planet is closer to the sun, it rotates faster than when it is furthest from the sun. And we finally now have proof that this is true because of conservation of angular momentum. So we are finally in a position to verify that this is true. Now this problem doesn't have the sun and a planet. What it does have is the Earth playing the role of the sun and a satellite playing the role of a planet. And this satellite goes about in an elliptic orbit around the Earth, and the position of closest approach, instead of perihelion, peri being closest, helion to sun, is perigee, peri closest, G for Earth, and apogee for apo furthest, G Earth. So what we're going to see is that when the satellite is closer to the Earth, it will have a VP which is larger than the A, the velocity at aphelion when it is furthest from the Earth. And we're going to use conservation of angular momentum to determine this. The satellite has a mass m, which has not been given to us, but what has been given to us is r sub p is 8.37 e to the 6 meters, r sub a 25.1 e to the 6 meters. So you can see that's nearly 3 times further. So this is an exaggerated elliptical orbit. And conservation of angular momentum in this particular situation will tell us that the angular momentum that the satellite has as a result of its orbit about the Earth at position A, apogee, should equal the angular momentum that the satellite has at position P, which is perigee. So let's see. I sub A times omega sub A equals I sub P times omega sub P. Well, what is I? We're going to model this satellite to be a point particle, so it's not rotating about its own axis, it's just a mass, which is rotating about a point which is r sub A squared. In other words, I equals mr squared. And omega sub A we can write as the tangential velocity at point A divided by r sub A. You see how everything comes back to us? And at perigee, we have m r sub p, and r sub p is squared, times v sub p over r sub p. So what can we cancel here? Well, this m cancels that m. This r sub a cancels one of those. This r sub p cancels one of those. And so now to solve for v sub a will be equal to r sub p over r sub a, once we divide out r sub a, times v sub p. And the reason I set this up here is that when we plug in our numbers, r sub p over r sub a, we find that we get 0.333, the value of the speed at perihelion, which, if you recall, was 8,450 meters per second. So then when the satellite is at apogee, at its furthest point, it's actually moving at 2,818 meters per second, or 1/3 the speed that it had at perihelion. Well, this concludes the last part of the problem-solving session for Chapter 12. Chapter 11. Until next time.